Hello everyone. In this video, we'll understand the fundamentals of logic. First, to start with, proposition, also called a statement. It is nothing but a declarative sentence which is either true or false, but not both. It will rain today. So that is basically a statement. So we can say it is a statement or a proposition. Bangalore is the capital of Karnataka. That is also a statement. Do you know where is Aditya? It is not a statement, but it is a question. 2 into 3 minus 5 is equal to 1. That is also a statement. Here, x square minus 1 equal to 4. Depending on value of x, it can change. The truth value or the false value will change. Truth value will change. Whether it is true or false will change. So it is not a statement. Come in is not a statement or not a proposition. It is basically a instruction, or you can say it is an order. So propositions are usually represented by small letters such as P, Q, R, S, etc. The truth or falsity of a proposition is called its truth value. If a proposition is true, we will indicate its truth value by the symbol 1 or T, and if it is false, by the symbol 0 or F. For example, consider a statement P where it says 2 is a prime number. Since it is, of course, 2 is a prime number, the truth value of this particular statement is either true or 1. You can use either 1 or true whenever you come across with the truth value as true. And the second example is statement Q, which says every triangle is a square. And actually, the converse is true. Even converse is also not true. Every triangle is a square is definitely not a true statement. So the truth value of this is 0 or F. I mean, if instead of triangle, if it is a rectangle, then the converse is true. Okay. The logical connectives. We can combine the propositions to produce new proposition by using the words or phrases like not, and, or, if so and so, then so and so, if and only if, etc. Such words or phrases are called logical connectives. So these are the logical connectives: not, and, or, if, dot, 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 then, dot, dot, if and only if, etc. The compound statements. The new proposition obtained by combining two or more proposition with the logical connectives is called a compound proposition or compound statement. In a compound proposition, the original propositions are called primitives or components. The truth value of the compound statement depends on the truth value of statements which are combined and on the logical connectives that are used. Propositions which do not contain any logical connective are called simple propositions. So let us see the first one, logical connective, which is negation. A proposition obtained by inserting the word not at an appropriate place in a given proposition is called the negation of the given proposition. The negation of the proposition is denoted by this symbol, an approximate symbol, P, or this symbol like this. Then writing P, it is read as not P, the symbol this or this denoting the word not. In other words, negation is an opposite statement. Let us see some example. Let the statement P be 5 is a factor of 10. Then negation of P is 5 is not a factor of 10. Truth table for negation is as below. So statement P can be either true or false. If it is true, then negation of P will be false. If it is false, then negation of P will be true. Next logical connective is conjunction. If two statements are combined by the word and to form a compound proposition, it is called the conjunction of the original proposition. Symbolically, if P and Q are two simple statements, then P inverted V, this is the symbol which is being used for and. So we read it as P and Q, denotes the conjunction of P and Q and is read as P and Q. For example, let the statement P be rainfall is exceptionally good this year. Statement Q is the rivers are flowing. Then P and Q will become rainfall is exceptionally good this year and the rivers are flowing. The conjunction P and Q is true only when both P and Q are true, otherwise false. The truth table for conjunction is as below. So let us consider all the possibilities for P and Q. P and Q both can be true. P can be true, Q can be false. P can be false, Q can be true. Both can be false. In that case, only in the first case where both are true, it will be true. Even if one is false, it will be false only. That is why here you find all F, because true and false, false and true, false and false, these are all becoming false. An example, let statement P be square root of 3 is an irrational number and statement Q be 8 is a prime number. Statement R be all triangles are equilateral. Statement S be 2 plus 3 equal to 5. Here P, that is root 3, is an irrational number and 2 plus 3 equal to 5. These two are true propositions, whereas 8 is not a prime number, so it is a false proposition. All triangles are equilateral is also a false proposition. So we say Q and R are false propositions, P and S are true propositions. Then in that case, P and Q, P and R, Q and R, Q and S, R and S are all false propositions. Only P and S will be a true proposition. Next logical connectivity is disjunction. Any two statements can be connected by the word or to form a compound statement called disjunction. Symbolically, if P and Q are two simple statements, then P, this V symbol V, Q denotes the adjunction of P and Q and read as P or Q. An example, let P be a statement which says Mumbai is in India and Q be a statement which says 1 plus 3 equal to 5. Then P or Q, you can write it as Mumbai is in India or 1 plus 3 equal to 5. The truth value of P or Q depends only on the truth values of P and Q. If P and Q are false, then P or Q is false. Otherwise, it is true. Even if it is one of it is true, we have to write it as true only. So the truth table for disjunction is as below. Again, we are writing all possibilities of P and Q. Then P or Q, whenever both are false, that time only it is false. Otherwise, it is true. Example, let P be, same example only we are considering. Let P be a statement which is root 3 is an irrational number. Q, which is said as 8 is a prime number. R, all triangles are equilateral. S, 2 plus 3 equal to 5. Here P and Q are, P and S are true propositions and Q and R are false propositions. We already saw that. Then P or Q, P or V, P or S, Q or S, S or V are all true, but Q or R is false because both Q is a false proposition and R is also a false proposition. So together, if we say Q or R, that is also false only. Next logical connective is a conditional statement, or we also called as implication. If two statements are combined by using the logical connective, if ... then ... means in between some sentence you may be writing if so and so, then so and so. Then the resultant statement is called a conditional statement. If P and Q are two statements forming the implication, if P, then Q, then we denote the same as P, then arrow mark Q, read as P implies Q. Similarly, The implication if Q then P is denoted by P arrow mark, Q arrow mark P read as Q implies P. The conditional Q implies P is not the same as the conditional P implies Q. In the implication P implies Q, the first one, that is P, is called antecedent, and the second one is called consequent. Antecedent can also be called as hypothesis, and consequent is also called as conclusion. An example, let statement P be, I have headache. Statement Q be, I will take aspirin. Then P implies Q will be, if I have headache, then I will take aspirin. The implication P implies Q is true in all cases except when P is true and Q is false. Only in that case it will be false, otherwise it will be true only. Means the truth table for implication is as follows. We are writing all possibilities of P and Q: true, 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 false, false, true, false, false. P implies Q. You will see where the first statement is true. In these two, first statement is true. Then you check the second statement. If the second statement is false, then only P implies Q is false. So here you may notice first statement is true, second statement is false. Only in that case it is false. The rest of the places it is true. Now coming to Q implies P, you consider first statement as Q, second statement as P. In first statement, where all it is true, in the first one and in the third one. In the first one, the second statement is true, so it will be true only. Only in the third one, it is first statement is true, second statement is false. That is why it is false. Rest of the things are true. Now, some examples. Determine the truth value of the following. If 5 is an even number, then India will win World Cup final. Means we are trying to now split it into two different statements because this itself is a conditional. So here our statement P will be 5 is an even number, and statement Q will be India will win World Cup final. So if the statement P's truth value is false, here in this case, 5 is an even number is false itself. So we need not check in that case the second statement's truth value. We can straight away conclude P implies Q is true. In the second example, if 3 plus 6 equal to 9, then Madhavan is the Prime Minister of India. Here, statement P, that is the first statement, is 3 plus 6 equal to 9. Second statement is Madhavan is the Prime Minister of India. So here, since the first statement is true, we need to check the truth value of the second statement, and we found that the truth value of the second statement is false. So the resultant implication will be false only. So that is what is written here. Statement P's truth value is true. So in this case, we need to check the truth value of statement Q, and since that is false, we can conclude that the truth value of P implies Q as false. Next, biconditional. Let P and Q be two propositions, then the conjunction of the conditionals P implies Q and Q implies P is called the biconditional of P and Q, denoted by P, both sides you will have arrows, P and then both side arrow Q, read as P if and only if Q. Biconditional is also called by implication. It is also read as P is necessary and sufficient condition for Q. Hence, based on this definition, since it is a conjunction, we say P double implies Q is equivalent to this symbol. When you write three lines, horizontal lines, we call it as equivalent to P double implication Q or biconditional Q is equivalent to P implies Q and Q implies P. The biconditional statement is true when P and Q have same truth values and is false otherwise. The truth table for biconditional is as follows. So we write all the possibilities as usual for P and Q. So, and then here P implies Q, we know already. If the first statement is true and second statement is false, then only it is false, otherwise it is true. That is the basis for P implies Q. Same way, Q implies P. If Q is true and P is false, then only this will be false, otherwise it is true. P Biconditional Q is nothing but the conjunction of these two. So first one, both are true, so it is true. False and true, it is false. True and false, it is false. True and true, it is true. Example, let statement B says, you can take the flight. QB, you buy a ticket. When I say P biconditional Q, it means you can take the flight if and only if you buy a ticket. Now let us understand what do we mean by converse, inverse, and contrapositive. Consider a conditional P implies Q, where P and Q are any two propositions. Then the opposite means Q implies Q is called the converse of P implies Q. Next, negate P implies negate Q, or not P implies not Q is called the inverse of P implies Q. Not Q implies not P is called the contrapositive of P implies Q. An example, state the converse, inverse, and contrapositive of the following conditional. If a quadrilateral is a parallelogram, then its diagonals bisect each other. Primarily, we need to segregate what is P statement here, what is Q statement here. So here P will be quadrilateral is a parallelogram, Q will be its diagonals bisect each other. Hence, the given statement is symbolically represented as P implies Q. Converse means we have to now write Q implies P, then verbal language it will be, if we will be writing first statement Q its diagonals. So you can't start with its diagonals. You may have to specify if the diagonals of a quadrilateral bisects each other, then it is a parallelogram. So here we don't repeat quadrilateral in the second statement because quadrilateral already applied in the already came in the first statement. That is the reason. Then comes inverse. You may have to write it in the form of not P implies not Q, which means in verbally it will be if the quadrilateral is not a parallelogram, then its diagonals do not bisect each other. Next comes your contrapositive, where you may have to write it in the form not Q implies not P. So in verbal language, it will become if the diagonals of a quadrilateral do not bisect each other, then it is not a parallelogram. Next comes tautology. What is the meaning of tautology? A compound proposition which is true for all possible truth values of its components is called a tautology. It means that it contains either 1 or t in the final column of its truth table. To understand this definition of tautology, we are having an example here. Prove that the compound proposition P implies Q biconditional within brackets not Q implies not P is a tautology where P and Q are any two propositions. First, we need to make a truth table for the given compound proposition like this. You write all possible values of P and Q. Then you find this P conditional, P implies Q, you write, in which you know P implies Q means whenever the first statement is true and second statement is false, only then it will be false. Rest of the places it will be true only. So here it is true. The second one it is false. Rest are all true. Then comes not Q. We have to write the opposite values of Q here. So when it is T, it is F. When it is F, it is T. When it is T, it is F. When it is F, it is T. Then we have to write this not P. So wherever P is there, that is here, we have to write the opposite of it. TT, so you wrote FF. Here FF, you wrote TT. Now comes not P implies not Q. So not P, wherever it is true in the first statement, that is in not P, and wherever F is there in not P, there only it will be false. Rest of the places it will be true. So this is true, this is false, this is true, this is also true. Now you can evaluate the final compound proposition, what it is. P implies Q, biconditional, not Q implies not P. So you take this column, that is third column, and the sixth column. Wherever both the letters are same, it will be true. If it is different, then it will be false. Here it is same, so it is true. Here it is same, it is true. Here it is same, it is true. Here it is same, it is true. That is why you may notice that the last column contains only Y. So this is a tautology. Next comes contradiction. It is also called as fallacy or absurdity. A compound proposition which is false for all possible truth values of its components is called a contradiction. It means that it contains either 0 or F in the final column of its truth table. Again, to understand this, we will have an example here. Prove that the compound proposition P or Q implies P. The whole thing implies Q or not Q under brackets is a contradiction where P and Q are any two propositions. So we need to make a truth table for the given expression. So we write all possible values of P and Q. Then next step is to find out P and Q. We know when both are true, only then it is true, otherwise it is false. So we wrote that. Next comes P and Q implies P. So this is considered to be the first statement. This is considered to be the second statement. If the first statement contains a true and then second statement has F, only then it will be F, otherwise it will be true. So everything is true now. Not Q, here it is, not Q. We wrote opposite of whatever is there in Q. So when it is T, it is F. When it is F, it is T. When it is T, it is F. When it is F, it is T. Then comes Q and not Q, means this and this. So when we do that, everything will be opposite, so everything will become F only. Now, P implies Q, the whole implies P, and then that whole thing implies Q and not Q. That is the given expression. If we compare, means here we consider this as the first statement, this as the second statement. Everywhere you may notice the first statement is true, second statement is false, the result will be false only. Since the last column contains only F, it is a contradiction. Then comes contingency, a compound proposition that can neither be a tautology nor a contradiction is called a contingency. To understand this, let us consider this example. Prove that the compound proposition P implies Q, whole thing implies P and Q is a contingency where P and Q are any two propositions. So we are going to make a truth table again, having all possible values of P and Q. So first we find this P conditional, P implies Q, we find out, wherein we know only the first statement if it is true, second statement if it is false, the result will be false, otherwise it is true. Then comes P and Q. In this case, only if both of the statements are true, it will be true, otherwise it will be false. We wrote that. So when you find out consider this as the first statement and this as the second statement, we may notice the first two will be true because only the last one you have first statement to be true and second statement is false. Only those things are false. So in the last column, we may notice that last column contains both true and false. So it is a contingency. Then comes your logical equivalence. What do we mean by logical equivalence? Two propositions P and Q are said to be logically equivalent if they have exactly the same truth values under all circumstances, or the biconditional P double implication Q is a tautology. It is denoted by P 3 horizontal lines Q. So now for understanding this, let us consider the following example. Prove that not of P double implication Q is equivalent to not of P implies Q and Q implies P. So first of all, we need to make the truth table for this left-hand side also and for the right-hand side also. See whether finally the left-hand side and right-hand side values are exactly the same or not. So first of all, we consider all possible values of P, all possible values of Q. Then we write the double implication P double implies Q, means P biconditional Q. So you know that only if these truth values are same, we will be having true, otherwise it will be false. So here it is same, so it is true. Here it is same, it is true. This one and this one is false. So the opposite, that is negation of this, not of P double implies Q, will become opposite sign of all this F, T, T, F. Next comes your, this is your left-hand side finally. Now we will be expressing this P implies Q. So wherein we may notice only the second one is false, rest of the things are true. Then Q implies P. Only the third one is false, rest of them are true. Now P implies Q and Q implies P. Only both are true means it will be true. So here and here it is true. Then not of this, I mean negation of this becomes this will be false, this will become true, this will become true, this will become false. So we may now notice that this RHS components and this LHS components and this RHS components are having the same truth values, hence the proof. So this is our some of the fundamentals of mathematical logic. In case if you find the contents to be useful to you, I request you to please like it, share it with your friends, and also subscribe to my channel. Thank you.